Good evening, everyone. Thank you for joining us tonight for the 2019 Michio Yanai Distinguished Lecture. My name is Jochen Stütz. I am the outgoing chair of the Department of Atmospheric and Oceanic Sciences. And I'm pleased to welcome you to this special lecture, which we started in 2014 in honor of Michio Yanai, who was an expert in tropical meteorology and a professor and an esteemed colleague in our department from 1970 to 2010. And it's also my pleasure to welcome Michio's wife, Yoko, and her sons, Takashi and Satoshi. Actually don't know, hello, who have joined us again this evening. And I would like to extend my thanks to the entire Yanai family for their generosity to make this lecture possible. And it's really private support, like the gifts from Mrs. Yanai, that is really important for us at UCLA to provide students, faculty, researchers with unique opportunities to engage with some of the best scientists in the field. And the gifts from Mrs. Yanai helps us to host this lecture, but also a visit in the department and another talk that was held yesterday, and scientists to engage with our students and with the faculty and exchange ideas and talk about research. This lecture series has grown quite a bit for those of you that have been here, and I say this every year, and that's true every year, that it's growing. I hope we'll see the day when we need a bigger room. And it just shows the interest that the public and also our students have in the topics we're covering here. And it's an exciting event, and the department, it's all the students sitting in the back, are very excited to be here. And with this, I would like to invite Alex Hall, who's a professor in the Department of Atmospheric Sciences and the Institute of the Environment and Sustainability, and the director of the Center for Climate Science at UCLA, and an avid cyclist, to introduce our speaker, Alex.
It's my pleasure to introduce tonight's Yanai lecturer, Dr. Inez Fung. Inez is a professor of atmospheric science at our sister institution to the north, University of California, Berkeley, where she was founding director of the Berkeley Atmospheric Sciences Center and the Berkeley Institute of the Environment. She's written groundbreaking papers on many topics in climate science, but she's especially well known for her work modeling the global cycling of carbon in the atmosphere, the ocean, and the land surface. The overarching goal of this research is to understand what is happening and what will happen to all that carbon that we're putting in the atmosphere through fossil fuel burning. So little questions like that is what Inez has been thinking about. She's been recognized for scientific excellence on numerous occasions by the American Geophysical Union. She was the Jewel Charney Lecturer for Atmospheric Sciences and the Tyndall Lecturer for Global Environmental Change. In 2004, she was awarded the Ravel Medal and was cited for fundamental discoveries on topics before most have even recognized them as important areas of pursuit. She is a fellow of the American Geophysical Union and the American Meteorological Society, and a recipient of NASA's Exceptional Scientific Achievement Award, and is a member of the US National Academy of Sciences, and I learned tonight, also recently elected to the Royal Society. So before we practically melt in her august presence, let us welcome her to UCLA and as our honored guest.
Thank you very much. It's really an honor to be selected to give the 6th annual Michio Yanai lecture. I thank Mrs. Yanai. I'm very honored and very pleased to be here. So I'm going to talk about a brief history of projecting climate and environmental change. I think many of us have been involved in projecting climate change. I've been doing projections since the early 1980s. And I have gotten a lot of questions. Why do you believe in the models? How, so I'm going to give a brief history of where we are. And we start with predicting weather. I want to, just before I start, to point out that I have selected pictures of clouds. I'm sorry that it got cut off. It's photos from the International Space Station, from Alexander Gerst, an astronaut on the space station, and he was there in 2014 and 2016. So these are fairly recent photos of clouds from the International Space Station. So the first thing is predicting weather. The first attempt to predict weather was by Lewis Fry Richardson in 1922. And he imagined, and you can see that, imagine a large hall like a theater, except that the circles and galleries go right around through space, usually occupied by the stage. The walls of this chamber are painted to form a map of the globe. Myriad computers, that's people who compute, are at work on the weather part of the map where each sits, but each computer attends only to one equation or part of an equation. The work of each region is coordinated by an official of higher rank. Numerous little lights display the instantaneous values so that the neighboring computers can read them. Each number is thus displayed in 3 adjacent zones so as to maintain communication to the north and south of the map. I think those of you who are doing the computation appreciate this is 1922. From the floor of the pit, a tall pillar rises to half the height of the wall. It carries a large pulpit on its top. In this sits the man in charge of the whole theater. He is surrounded by several assistants and messengers. One of his duties is to maintain a uniform speed of progress in all parts of the globe. Many of us appreciate that very much. In this respect, he is like the conductor of an orchestra in which the instruments are slide rules and calculating machines. So that was 1922. So the first experiment by Richardson was a grid over Europe. And so you can see the temperature. So you predict the pressure and temperature. So changes in the temperature would change the density. So changes in density would change the pressure. Changes pressure in different places will change the pressure gradient. That would change the wind, and the wind will change the temperature, and off it goes again. So the first experiment to calculate the change in pressure, he predicted 145 millibars in 6 hours when what was observed was much, much smaller. So it was an utter failure, the first experiment. While the template was set, it was not successful. Many people have written about this, that Richardson's error is the computational instability. You can figure out how strong, how fast the winds are going, given the grid size, that he should have taken a time step of 11 minutes, and my gosh, he took a time step of 6 hours. Of course he would blow up, okay? Of course. However, Richardson should have blown up, but he didn't because he only took one time step. So it was not the reason the model has not yet blown up. So what Richardson said is that it was the use of unbalanced initial data that was his fundamental error. So now we're talking about the initial conditions for the weather forecast, and because he was doing wind, he had to get wind, he had to get temperature, pressure, etc., and they were not balanced, they didn't satisfy his equation, so that was his fundamental error. So now we come to UCLA. Joe Charney, he was my thesis advisor. And for his thesis, he did the dynamics of long waves in a baroclinic westerly current. And that was 1947 when the paper came out. And so that was, I don't think he was thinking about weather forecast. So in his letter to Phil Thompson in 1947, Charney wrote, In the terminology which you graciously described to me, we might say that the atmosphere is a musical instrument. Again, so this is harking back to Richardson. It's a musical instrument on which one can play many tunes. High notes are sound waves, low notes are long inertial waves, and nature is a musician more of the Beethoven than of the Chopin type. He much prefers the low notes and only occasionally plays arpeggios in the treble and only with a light hand. The oceans and the continents are the elephants in the Cézanne animal suite, marching in a slow, cumbrous rhythm, one step every day or so. Of course, there are overtones, sound waves, billow clouds, gravity waves, inertial oscillations, etc., but these are unimportant and only heard at NYU or MIT. So then in November, same year, then he started focusing on weather forecasting. The main reason is that I have been brooding about the problem of numerical computation ever since coming to Norway. And I think I have come up with an answer to at least one of the most vexing aspects, namely the practical impossibility of determining the initial vertical velocity and acceleration fields with the necessary accuracy. All of us who have been around remember how many bits of the machine and double precision for the vertical velocity. This was 1947. The solution is so absurdly simple that I hesitate to mention it. It is expressed in the following principle. Assuming conservation of entropy and absence of friction in the free atmosphere, the motion of large-scale systems is governed by the laws of conservation of potential temperature and potential vorticity, and by the condition that the field of motion is in hydrostatic and geostrophic balance. This is the required filter. It really does eliminate the small-scale noise, and the small-scale noise was what got Richardson the wrong answer. It is possible to justify the approximation used in deriving the filtering principle by method of scale analysis, etc. The value of the filter for numerical computations lies in the fact that the equations of motion can now be easily reduced to a single equation in pressure alone. By having a single equation in pressure, then you only have to observe pressure. You don't have to observe temperature, you don't have to observe wind, etc. That was Richardson's problem. So the first successful numerical forecast was done in Aberdeen at the Naval Testing Grounds in Aberdeen, Maryland. So they had a grid over US. This is Charney here. This is Norm Phillips. 24-hour, 48-hour forecast. It took them 33 days to debug the code and do the forecast. So they actually made a 24-hour forecast in 24 hours. And so he figured out the quasi-geostrophic equations, which I just described to you. The computation was done on an ENIAC with fewer than 10-word read-write memory. So this is a function table. Imagine this is your thumb drive. Okay, and people who work on this is read memory. So to make a forecast, it takes 16 operations in each time step. You shovel the cards in the order in the function table, okay, the punch cards, and so then you can see, and then you have to organize them so that all in the 10-word memory are all the things that you need for the computation, and then it was spit out, and then they put out output, and then you have to now get the output and then get new cards and rearrange the cards in such a fashion that the 10-word memory is computing the things. You have all the cards in the 10-word memory. So it takes 16 of these, and I'm sorry the bottom got cut off. In George Platzman, in this bulletin article in 1979, said they actually did a jig. You know, while the key punch was going, they would wait and they would dance a jig. Okay, da-da-da, da-da-da. Okay, so you can dance while the key punch was going. So it was a very successful forecast. It was done 24, as I said, in real time, 24-hour forecast. They didn't get enough time. They had to petition for additional time so that they could continue the debugging. They had not debugged the code until when the time was up. So anyway, so here, with the successful weather forecast, we now have Nimbus, we have satellite observations, and this is the granddaddy of current Earth observation fleet in 1964. It is the first observation of the hurricane in 64, and now we are very familiar with satellite observations, but this is 64, and you can see the first map of sea surface temperature in 1978. So with these, now we have rainfall, sea ice, ozone, marine productivity, and many other parameters. So we are also used to seeing satellite observations. That this was really exciting in 1964 when the satellite data came in. And so now with the satellite data and the physics of the numerical weather forecast, the quasi-geostrophic equations, I think all of us are very familiar with what is going on. And so this is, I always check windy, so this is the forecast for June for this weekend. So you can see, you can download this, you can check the clouds, you can check the aerosols, you can check rainfall and everything. So this is the entire ECMWF output that is now online. I have it on my phone and I check it every hour, okay, to see what's going on around the globe, okay? So this is now operational, and this is a long time since 1947, and a lot of things have gone on. We have more than 10-word memory in our phones, and we have obviously observations of everything. So that's weather forecast. And weather forecast, you know, we do it in, you know, a week is okay, 2 weeks is on the fringe of whether the weather forecast is good or not. So I'm going to move on to a slightly longer time scale, which is predicting El Niños and La Niñas. And I like to show all these clouds because I really like the clouds, the view of clouds from the space station that the astronaut took. So the El Niño and La Niña is a coupled system, atmosphere-ocean system, and it was first proposed by Professor Bjerknes, also of UCLA, so that it's the eastern, what happens is the eastern to central equatorial Pacific, there's warmer sea surface temperature, weaker westerlies, and so that Klaus-Wertke also showed that sea level in the western Pacific rises before the warm phase of the El Nino, and so there's a recharge oscillator. So all of that is just isolated pieces of observation of what description of what El Nino was about. So Mark Kane, I'm sorry that this got cut off. Mark Kane, who was Joe Charney's student, did a thesis which is waves in the equatorial ocean. And this follows from Matsuno's work, and I think Professor Yanai worked with Professor Matsuno early in Japan. So this is following Professor Matsuno's work on waves in the equatorial stratosphere. So here then we have wave number and frequency. So in the equatorial Pacific, we have Kelvin waves and then Rossby waves. Okay, and this is just a theoretical calculation of what happens to these waves. Okay, when the wind blows, there are these waves. There's a family of Kelvin waves that propagate eastward. The Rossby waves propagate westward. But at the same time that happened, then Dave Halpern started lowering buoys. And so this is a fantastic, to me it's a fantastic. Before that it is oceanographers going out to sea and they measure whatever they measure at sea. So there's no long-term observations of the ocean. So what Halpern did was to lower a railroad tie to the bottom of the ocean, and the wire had to be 4 meters shorter than the depth of the ocean, so that the currents don't, so that it's the wire would be taut, with the currents, and then by hand they put on fairings, okay, so that it would. Anyway, so then you attach temperature and salinity and pressure sensors along this. And so now with these buoys, then we start the beginning of the global tropical buoy array. And so what we have then is starting with Professor Wertke's identification of what the processes are, with the theory that Kane and Sarachik came along with, and now the observations, then we have, oops, this got cut off. So we have the theory, we have the observations, and George Philander had the paper that talked about unstable air-sea interaction. So basically when the wind, normally the wind blows from South America to Asia along the equatorial Pacific. So sea level would be higher over Asia than South America. And so when the wind slackens, then the ocean would slosh, and here goes the Kelvin wave going that way, okay, and then the Rossby wave going westward, okay. So then we can have all of these working together, and that changes the sea surface temperature, etc. And so what Mark Kane did with his student is to create the first model that repeats itself, so that you have the wind weakening and the sloshing of the ocean, sea level rise, sea level changes, the sloshing of the sea level from west to east, okay, and so it repeats itself, so you can see the wind stress changing with it. So this is fantastic, because this now, and you note the time is in years, okay, so then we now go from weather forecast of weeks now to seasonal forecast. Okay, seasonal forecast, I think many of you in the audience know, it is not an initial value problem, it's a force problem. Okay, so you're looking at the state of the atmosphere, and you're looking at the forcing and changes in the couple instability of the atmosphere-ocean system. So now it's operational forecast. You have observations here and different groups. You have dynamical models like what I just talked about with all the ocean dynamics and the atmosphere. And then you have statistics, so there's a whole swarm of predictions there, and one of them is correct. And so what we see, okay? And so what we see here is that, so then you can look at the sea surface temperature. Now with satellite observations, we can see very clearly sea surface temperature anomalies that's warmer. That means that the warm water from the west has come eastward, etc. So we can now look at anomalies, and we actually make seasonal forecasts, and there are many groups doing the seasonal forecast. So we've gone from weather forecast to seasonal forecast. And so now we talk about projecting climate and Earth system changes. Very crucial to all of this, all of you know the CO2 curve, Mauna Loa CO2 curve. Dave Keeling, professor at UC San Diego. His PhD, he did his PhD at Caltech. Here I'm talking to the students here. His PhD thesis is to study uranium in granite. He was in the geology department. And he built a vacuum extraction system to isolate the CO2 gas from each sample of air and acidified water. And so he asked the question, is CO2 air constant? Because he had to equilibrate to the CO2. So he found an old text, old paper in the library, and he said Caltech, so he had the people build him the same instrument. And so then he went camping. That was what he wanted to do. Okay, he went camping at Big Sur State Park. And so he went camping and camping, okay, so that was what he wanted to do. So he would come out of his tent and measure. So here's the first CO2 variation from Dave Keeling. So you can see already the seasonal cycle, and this was in 1957. And what Dave wrote was that why did I devise such an elaborate sampling strategy? By the way, he never published his work on uranium in granite. So he said, why did I do such an elaborate sampling strategy, have them build me the instrument just to ask if the standard is actually constant, the CO2 in the air? when my experiment didn't really require it. The reason was simply I was having fun. Okay, I just want to say that to the students, okay? Dave Keeling didn't know where he was headed, okay? And so in the 1957, in the geophysical year, Roger Revelle, many of you know Roger was the director of Scripps Institution of Oceanography in San Diego, and Roger has done, well, anyway, so International Geophysical Year, and they suggested measuring CO2, and Roger said, I heard of this young man at Caltech who could measure CO2. So that changed Dave Keeling's entire career, okay, and this is the familiar curve of CO2 when Dave Keeling went up to Mauna Loa Observatory in 1957. The CO2 concentration was about 15 parts per million, and today it's over 400. You can see very regular, the steady increase in CO2 in the atmosphere. So, and this is what we've been concerned about, the climate change, because of the CO2. Anyway, so, but if you look closely at the CO2 curve, you can see that there's a regular oscillation. We call that the breathing of the biosphere. So it peaks at Mauna Loa, far away. It peaks in May, and it bottoms out in October. And it's repeated. It's very regular, as you saw in this figure. So what happens here is that in May, the growing season starts in the northern hemisphere. So the plants start photosynthesizing CO2. So you can see the withdrawal of CO2 from the atmosphere, and then there's decomposition that returns CO2 to the atmosphere. So this is very regular. We're seeing the biosphere, the photosynthesis, decomposition, year after year. When I started working on this, I was trying to explain this. I didn't have any data. So I guessed growing season, so northern hemisphere. I guess when photosynthesis will start from my allergies. So this is my sneeze function. It's actually in the code. This is my sneeze function, and that's my rot function, because when you go hiking, you can see litter, you can see decomposition. So that's my sneeze function and my rot function. And so you can see that even though I assign the same amount of CO2 uptake and release, that there's overlap between the uptake season and the release season, the decomposition and the photosynthesis. So what the atmosphere feels is the hashed part. So in the subtropics, you can see that it's the same amount, but a longer growing season, and if we assume continuous decomposition throughout the year, and so the difference is very small. So in the tropics, when we assume that the CO2, the growing season is not that seasonal, so the growing season is all year round, and the decay season is all year round. So even though there's a lot of CO2 going back and forth, this atmosphere doesn't feel much of it. Okay, so there's not much of an amplitude. So this was fine to make up these sneeze and rot functions. And so what happens here is that Jim Tucker, and this is another PhD thesis. I'm talking to the students in the back here. Okay, the PhD thesis, they had no clue what he was doing at the time. So what he did was he had handheld radiometers, and he was studying grasslands. So then he is trying to figure out, when the grass is green, what the spectral signature of the grass is. And he also had a paper on the sensor design. So this is the normalized difference vegetation index, the NDVI. So if you look at this curve, I'm sorry that it got cut off. This is the visible part of the spectrum. This is about 2 microns. So you can see here what looks like a square root sign here. This is green leaves. Okay, green leaves are green because they reflect in the green. They absorb in the red and the blue. Okay, so here is the infrared, about 0.7, 0.8 micron to 1 micron here. So the plants don't need any more energy, cannot use that energy, so it's reflecting most of that energy. Okay, so you can see the water vapor. So the satellite now we're using the near infrared, which is this, and minus this, the visible part here, and normalized by the difference. So you can see that when there's green vegetation, the difference would be high. And if we have bare ground or water, then there's not much of a signal. There's not much of a difference. And so this you see now, the background of a lot of TV news desks, it's the global map. You see the desert, you see the forest, and this is all the normalized difference vegetation index, which grew out of Jim Tucker's PhD thesis. What he also did, something which I was shocked, was that the NOAA at the time had the wavelengths together. Okay, so it would not be very useful. You need the two bands separated so that you can do the difference. And as a postdoc, he went down to NOAA headquarters. He was a postdoc at Goddard Space Flight Center. He went down to NOAA headquarters and said, please separate the bands. They didn't pay attention the first time, but the second time they did. And so then he did it on the weather. And this is so clever, to do it on the weather satellite, and he processed all the data himself. And so this is the first, it's familiar to you now, but for me, it's like the first time we see the whole continent, the photosynthesis of the whole continent. And this is Africa from space, okay, using the satellite data, so you can see the desert and the rainforest here, etc. So now you're familiar. You can see the green wave going. You can see satellite. Now we have 30 years of observation of the greenness of the greenness of the planet, and we're using this to forecast locust outbreaks in Africa. We're using this for crop monitoring. We're using it for all sorts of other ecological applications. So now for me, then I mapped this. I averaged the NDVI, the greenness index. So you can see this is 3 years. From 1982, this is the first data, from 82, 83, 84. So you can see the time. This is north to south. So you can see the growing season, okay, when the NDVI is high. And you can see the tropics where it's growing. The growing season is throughout the entire year. So this is throughout 3 years. There are variations. Okay, so and you can see southern hemisphere is out of phase. So this is very exciting to see the whole globe, photosynthesis of the whole globe, multiple years. This was 3 years. When it came out 2 years, I thought it was Jabba the Hutt. If you cut off that side, we call that our Jabba figure. But anyway, so now we have 30 years, and you can look at changes. You can look at land cover change. So when I put the Keeling curve, the CO2 at all the other stations, then you can see overlap that when it is green is when the CO2 in the atmosphere is decreasing. So this totally confirms, my sneeze function, okay, that when this photosynthesis is the magnitude, is the right magnitude. So you can see now the greenness index. You can see the between seasons. I just put out that you can see the Amazon is green all the time. There's the boreal forest that's green in the northern summer, and it's fairly weak in the northern winter. So now we have 30 years, and we can do all sorts of stuff with it. So now with the CO2, with the climate system, with forecasting the weather, looking at the physical changes in temperature and precipitation, the physical system, now we can add in the biological system, the carbon system, into the climate. And so you can see this was what we did from the recent United Nations, the IPCC, the multi-international comparison. You can see this. CO2 is increasing. If I don't allow temperature to change, okay, more CO2, the plants will grow bigger. Okay, this is what happens in greenhouses where they grow tulips and roses. Okay, so they have higher CO2. There's always abundant light, abundant water, there's irrigation and abundant fertilizers. So then when there's higher CO2, the plants grow bigger. And you can see that if just higher CO2, there's a gain of carbon on land in all the places where photosynthesis is happening. But if we now let the CO2 and let the climate change, then as the CO2 increases, the climate is going to get warmer. There's going to be changes in the precipitation pattern, and that's going to affect decomposition, not just photosynthesis, but decomposition. So in all the models that contributed to this calculation, there's a loss of carbon. Okay, and this is where while there is, if you just look at the photosynthesis part, yes, there's an increase, but you have to look at the entire ecosystem. So the warming climate is accelerating the decomposition, okay, and so that returns the CO2 back to the atmosphere. So I want to switch now and talk about something that I have skipped, because all of this, talking about plants, talking about the climate, what is most important to us is water. We're the only planet with 3 phases of water, and the changes from liquid to solid to vapor is the dial of our entire climate system. So before we get rain, we have clouds, and this is another beautiful picture from the space station, and you can see towering cumulus clouds here. And so it brings me to Professor Yanai. I have so many papers, favorite papers by Professor Yanai, and I just picked one today. And this is the determination of bulk properties of tropical cloud clusters from large-scale heat and moisture budgets. And I just want to point out this was in 1973. So in that paper, he analyzed the data from Marshall Islands in 1956. And so he says, consider an ensemble of cumulus clouds like this, with tall clouds, high clouds, mid clouds, and low clouds. These clouds are embedded in a large-scale motion system, and we assume that the activity of the cumulus clouds is statistically in equilibrium with the imposed large-scale motion. So this is saying the clouds are not just beautiful, you write poems about it. I look at it, I look at the night sky, I look at the evening sky, but the clouds are doing something, okay, and they're there because they are in equilibrium with the large-scale environment. So obviously, individual clouds will undergo their own life cycle. However, we hypothesize that over a time scale describing the behavior of large-scale motion systems, the cloud ensemble maintains the heat and moisture balance with the environment. So the clouds not just are pretty, not just they are sooner or later there will be rain. In terms of the heat and moisture, the whole balance of the atmosphere, the clouds are so crucial in maintaining that balance with the environment. And so what he continued is that the most important conclusion of that study is that the cloud mass flux, this is going up, this is a cloud, there's entrainment bringing in dry air from the environment, and then detrainment, the moist air leaving the cloud, so that the most important conclusion is that the cloud mass flux, that's the blue one going up, exceeds the mean vertical mass flux required by the large-scale convergence, thus causing a compensating sinking motion between the active clouds. This was so profound in 1973. We just look at single cloud. He's looking at the entire cloud system, looking at the equilibrium with the system, but not just that, talking about not just the clouds going up, which is what I would see, and I avoid planes bouncing around this is what we don't like when we fly around. But the important part is that there's a compensating sinking motion between the active clouds. And so the large-scale heating of the environment is primarily due to the adiabatic compression in the compensating downdraft motion, the cooling due to re-evaporation of liquid water detrained from the clouds, that's here, the detrain that leaving the clouds, also an important factor in the heat balance of the environment. So counteracting the drying due to the environmental sinking motions are the large amounts of water vapor and liquid water which are detrained from the clouds, especially from the low clouds. Now this is the sentence I have underlined. That's the shallower, non-precipitating cumulus clouds by their vertical transfer of water vapor supports the growth of deep precipitating cumulus towers. I think those of you working on clouds, this is 1973, okay? We're now talking about the cloud resolving models. We can do this, and we have warm sea surface temperature, and we need, the shallow clouds, the high clouds, etc. But this is 1973, and this anticipates everything that's going on today, to me. A lot of the stuff of organizing self-aggregation, a lot of the studies on cloud processes. And so this is a very simple, not simple, profound idea that came out of Professor Yanai's analysis of the Marshall Island data in 1956. So this is fantastic to me to see this in 1973. And so together with Professor Akio Arakawa here, also in this department, so that all the ideas of multiple layers, multiple clouds, an ensemble of clouds, the Q1, Q2, the mass and the moisture and heat balance, all of those are now incorporated into climate models to project changes in the climate system. And so also the idea of quasi-equilibrium, the fact that the clouds are in equilibrium with a large-scale environment which came out of this analysis is now what we are accepting as the thing, the principle that's guiding a lot of the clouds. So this is so anyway, so what I show now is the 2013, the latest IPCC, and so you can see the ideas, the Professor Yanai's idea, then the warm ocean, there's cumulus clouds, but here you see the large-scale subsidence, and so they're warming, the subsidence, there's warming with the subsidence, and you can see the high clouds, the and the spectrum of different shallow clouds and high clouds. And so when we look at this and do the projection also now from the recent IPCC, then you can see that as climate changes, the high clouds are expected to increase. The Hadley cell is projected to expand. And so here we have a projection of the poleward shift of storms. And I think all of us can relate to what is happening in the weather last week or this week and in this particular summer. It's been, we've been getting drier. Okay, the Hadley cell expanding, the sinking motion is coming towards us or closer to us. So we're getting drier from the expansion. And now with all the tornadoes in Massachusetts, in the Midwest, going north, further north, and now you can see a lot of these, a lot of the projections that are coming true here. I want to mention here that I've been working on climate models since the 1980s and climate projections. And I think the outline of what the models projected in the early 80s have not changed. In the decades since, the results have gotten higher resolution, more richness about local, regional changes rather than global or very large-scale changes, but the outline of warming, of sea level rise, of changes in the precipitation pattern, of more extreme precipitation, longer droughts when the rains come, it is more heavier. All of those we talked about in the 1980s. And to me, talking about from there to here, what the credibility of the climate model is built on the physics that I started to mention, a sketch for you, from the weather forecasting model, from the physics of the flow, and from the coupling with the ocean and, you know, the cumbrous, the saisons animals, okay, the ocean, and now coupling with the carbon cycle and the ecosystem. All of that is based on sound observations, and also on theory and brilliant thoughts that were done before any of the data came in. So here is a projection, the transient from all the climate models from the last IPCC. So what you see here is that relative to 1870, this is the cumulative CO2 emissions since 1870, and this is the temperature change since 1870. So you can see that there's a monotonic relationship. Okay, the more emission we have, the higher CO2. Okay, the higher temperature, the greater warming. So when I say warming, warming to me is just a shorthand of the changes, not just in temperature, but temperature extremes in terms of precipitation extremes and ecosystem changes, etc. So this is relative to 1870. And so if we want 1.5 degree warming relative to 1870, then the cumulative emissions since 1870 should be about 615 petagrams. And so it's the same graph now plotted relative to 2015. So now 0 is in 2015. Then to get to 1.5 degrees, we only have about 100, at the rate that we are emitting CO2 to the atmosphere, we have a decade, less than 2 decades to reach 1.5 degrees. So this is an urgent issue. And while I've been working on it, I don't mean to depress anybody with this, but I think that what I'm trying to say here is that based on the physics, based on the chemistry, based on a lot of the foundational understanding of the atmosphere and ocean system that started here at UCLA in this particular department, in particular here with Charney and Professor Yanai and with Bjerknes here, that we have the sound foundation and there's credibility in the projections that we have going forward. And so what we do about it is up to us personally and together. But I want to end here with a quote from John Tyndall. Tyndall is a British gentleman who made the first direct measurement of CO2 as a greenhouse gas. Okay, so he made the first observation. And he wrote, "I believe even before an audience like the present, to uncover to some extent the unseen things of nature, and thus to give not only to the professed students in the back, but to others with the necessary bias, industry, and capacity, an intelligent interest in the operation of science." So I hope to give you how the people didn't think about, they didn't think about what the uses were, but they were just interested. Keeling was just having fun. Charney was just thinking about his mathematics, his hypergeometric functions. So time and labor are necessary to this result. Students work harder in the back. But science is the gainer from the public sympathy thus created. So I want to thank you very much for the honor of this. This is another picture of clouds from the International Space Station. And every time I look at these pictures, I think about Professor Yanai, because I like looking at clouds, and I really like his papers on clouds and what clouds do. And I'm wondering what Professor Yanai would say that they are doing here, Okay, every picture I look at, I would ask, what would Professor Yanai say? It's not just pretty, not just carbon vortices. I can see Jim McWilliams saying carbon vortices back there, but what are they doing to the atmosphere? You know, so I thank you very much.
We have time for questions.
Thank you so much for this review and overview of the history from weather to climate. And one of the messages we get is really the science is sometimes the best science would come from fun or unintended consequence. But yet, in today's environment, funding environment, and that is becoming harder and harder. I feel especially for young people and at the peak of their creativity, and they're actually have to deal with very little flexibility in terms of survive or succeed in our current research and academic system. So what can we do to improve? Well, there are many things one can do, but I always tell the students that remember why you are in science and not doing something else, okay? You enjoyed it once upon a time when you were in school, and you're enjoying it now. So what I would do, what I do myself is that I leave myself some hours, you know, some time every week, which is for my own amusement. I would look at something. I would do what I have to do. I mean, there's lots of things I need to do. I'm behind on all sorts of deadlines and proposals and stuff. Okay, but I still leave some time for myself to read stuff I don't know anything about, to learn something new, because it is fun. Okay, this is how I keep going, is that it is fun. So then with the current environment, what I tried to do yesterday was to say that even though there are relevant, there are societal, there needs to do with climate mitigation, to do projection, to do all sorts of things. In all those needs, there are interesting questions that have not been addressed at all. Okay, so one could find doing all the useful, all the useful science, there's also interesting unasked questions. And so it's just looking for those questions that I can spend time on, okay, sneak time, and so I can read something and learn something new and think about new questions. So you have to, it is an exciting, I think we're here because I look at pictures like this and I think what a marvelous system, nature is so marvelous. I would not have dreamt of pictures like this, okay? So nature is just beautiful and marvelous, and there's so many mysteries. For me, every time I think I'm arrogant and I think, oh, I will go and solve this problem, nature always says no, wrong, do it again, okay? So to me, it's like a puzzle. But the crucial thing is that you are here for a reason, for the students in the back. You're here for a reason. You enjoy the science, you enjoy looking at the atmosphere, studying, trying to understand the atmosphere. So yes, there's part of me, yes, there's a large portion of my days, my weeks are doing useful stuff, okay, that is relevant. But there's also part of me that's doing something that's fun.
What do you think are the biggest challenges for the next 10 or 20 years that you hope may be solved in the field?
I think it's the will to do something. And I get nervous when I look at the projections, is that to deal with change requires a will to admit that there's a need for change. I think Jim McWilliams and I were on a committee in 2001 when President Bush came into office about climate science. And so there, one of the questions from the White House was, have scientists determined a safe level of CO2? And so you can say, oh, historically, and it was like this and like that, but people, since civilization, it has not been as high. But then the answer actually is safety is defined by the readiness of the infrastructure to deal with change. And so this is where I feel, I feel nervous, and sometimes I lose a lot of sleep over the figure I showed you. And so this is the political will and the people's will, okay, to do something about it.
Well, on this question, there's so much the human population can do as far as reducing our greenhouse gas emissions with our cars and
Yes.
how we use gas. What is industry doing to take out the CO2 out of our atmosphere? Is that really a possibility? Is that a solution?
Well, there's several answers to that. The large companies making more efficient appliances, and this is like another successful California story. Art Rosenfeld, who was the energy commissioner for California for many years, he was the one, when he was a professor at Berkeley and at the Lawrence Berkeley National Lab, he was the one who gave us Energy Star for all the appliances, so that so then you can also see, I don't have the figure, I can show you later, that while the refrigerators have increased in size, the energy efficiency has actually decreased. I mean, energy, the consumption has decreased. And so now what is limiting the size of refrigerators? Does anybody know? The size of doors. Okay, when you renovate a house, how big a refrigerator you can put in is determined by the door. So anyway, but to answer the question, so a lot of appliances are now made much more energy efficient, and I can see that in just last 10 years, everything more energy. So that is one way, not just personally doing something else, doing energy. Conserving energy, but also large companies. And I read Walmart now has a sustainability program that will track the carbon footprints of the entire supply chain. So whether they are successful is too early to tell. McDonald's now has a sustainability program. Again, this is too early to tell. Okay, but it's a positive move that large corporations are thinking in that direction. So to the second part of your question, there are new research projects, I think, and even commercial projects to try to take CO2 out of the air. So yes, they can do it. In Switzerland, there is one, Climeworks. There's one in British Columbia, Squamish, on the way up to Whistler. It's out there, and it's with David Keith, who's a professor at Harvard. And all those are, to me, it's like we have to try, okay? Whether it is scalable, whether it would work or not, I cannot tell, okay? As I see with the large corporations, I don't know. But I think that the science goes on, and I'm hoping that one of these engineering solutions may work, and so we just hope, right? Students, I'm looking at the people in the back, right? The future is in your hands. Yeah.
Speaking of the future, I fail to grasp a sense of catastrophe in your presentations. At the level of climate, I see smooth curves that slightly differ from one from the other, but I don't see a prediction as to atmospheric evolution towards either Mars or Venus. Now, that's for the climate.
Yeah.
And I also would like to backtrack to weather, thinking mostly about the Sandy hurricane.
Yes.
Where weather forecast models came into conflict with one another. Some predicting a turn towards the Atlantic
Yes.
Ocean,
Yes,
and some predicting a turn towards New Jersey.
yes.
And I don't know how, between EMCWF whatever, and MM5 whatever, and FV5 whatever,
Yeah.
what the resolution is, because there is a very clear sense of catastrophe.
Yes,
The hurricane did hit.
yes,
And nowadays, when we come, not to the past, but when we come to today, I see a total failure in the weather forecast models in terms of their ability to predict the amount of rainfall. Texas is an example. The village in southern France in the Aude department that got completely wiped out, not because the hydrologists didn't do their job, but because the forecasters didn't do a good forecast of the amount of rainfall. And the way we talk of El Nino and La Nina and all of that, but hey, we got those atmospheric rivers coming from
Yes.
the Pacific Ocean.
Yes.
And I didn't see those predicted. So I sense catastrophe, and in your speech, the lack of catastrophe.
I was trying to build the fundamental basis of where we could spend later on. I could show you all the catastrophe stuff I didn't show in my talk. Okay, so I just decided not to give a depressing evening to everyone, but we can actually talk about the success or the failure of all the weather forecasts. But I think you should think about everything as a probabilistic system. It's like rolling of dice, okay? So yes, we look at even now the weather forecast, okay? So the weather forecast, we make, somebody should correct me, 100 forecasts, okay? There's an ensemble of 100 forecasts, and we actually forecast the error in the forecast, which you don't see, okay? But we do see, okay, the error in the forecast. And so then, when you look at the 100 forecasts, many of them actually got the hurricane, and many of them, okay, so then it's just the average, you know, so you don't know, because of the nonlinear, the complicated system, you don't know, you know, Ed Lorenz, the flap of a butterfly's wings in Brazil, right, the tornado in Texas, you don't know a lot of the turbulence and all the fine scale and how that would propagate to the larger scale. There's still, as I said, there's still physics to be learned. Okay, but when we make forecasts in the 100, let's say 100 forecasts, many of them are correct, but we don't know which. Okay, we don't know which. Okay, so this is where we look at the ensemble of forecasts, and so the average will average the good and the bad. Okay, hindsight, we can go back, and this is how a lot of weather forecast improvement has gone, is to look at the error. You just track the error every day, every forecast, and then see if there's a systematic pattern to the errors, and then you can go forward. Okay, the ECMWF, so you can remember, I think of it as early closing Monday, Wednesday, Friday, so you'll get that right. Okay, so ECMWF, so you can, ECMWF have a higher resolution model, 9 kilometers, okay, and they have dedicated computers, and this is one of the challenges, and I think our government finally heard that the NOAA computers are not comparable to what they've got, et cetera, et cetera. So they can do higher resolution. Higher resolution is not just the space, but you can capture the nonlinear interactions of the flow. Okay, so there's a lot of stuff. Okay, so lots of things. Atmospheric rivers. Yes, we can talk for a long time about all those. Yes, we cover a lot of those. A lot of them remain questions for students in the back. Okay, research questions. But we have come a long way since 1947. And that started right here at UCLA.
Your one big thread in the talk was the history of model development.
Yes.
And you showed that scientific communities pretty definitively identified humans as playing a big role in climate over the past few society has to respond. And my question now is, what should the scientific community be doing? What should our model development activities be going forward, given that we've more or less resolved this climate question? What's the future of model development?
To me, a lot of it is we just say, oh, this is if we do this, this will happen. So it's a fairly straightforward. What I'm starting to think about is if we do mitigation, okay, if we plant trees somewhere, what trees, what species do we plant, where do we plant them, and whether they will sequester the carbon, will they contribute to warming, further warming, or will reduce the warming, how they would use water, et cetera, et cetera. So there are new questions that come in as you say, how do we do not injecting aerosols into the sky, but just there's many things that we can do. We ask the question in a different way, okay? And so that requires a different approach to dealing with those questions.
Three more questions. The back row currently for Rich.
Hi, Rich.
Inez, I'm not a student.
But you can still be learning.
Yeah.
Because I learned a lot today. But I have a simple solution to a serious problem that you mentioned, and that is the refrigerator size problem.
Yes?
Because I currently have 3 refrigerators.
Why do you need 3? Huh? You have to. That's why they have refrigerator drawers, right? So you can have a lot of those. Yeah.
We came about carbon dioxide million years ago. Carbon dioxide million years ago.
Yes.
We're thinking about right now. But should we care about what paleontological data for carbon dioxide?
Carbon dioxide, the continental configuration is not the same like what we have today. Okay, the continents have moved around. So the Arctic, there were crocodiles in the Arctic. What is the Arctic now? And carbon dioxide has been very high. Okay, so that's a lot of those things happen on million-year time scale. Okay, million-year time scale. So you can imagine, once upon a time we had a snowball Earth when okay, and then it took millions of years for so there's the plate tectonics, the subduction of the plates, and then the CO2 comes back out through volcanoes. Okay, so just for reference, we are emitting about 10 gigatons carbon per year. Okay, the average volcanic eruption is about 0.2 to 0.3. Okay, so you wait millions and millions of years, so then the ice melted, et cetera, and CO2 came up. We don't have the luxury, okay, of the geologic carbon cycle going in and the sediments, forming sediments, et cetera. So we don't have that luxury. So in human history, the CO2 has not been this high. So when you talk about higher CO2, yes, from that geologic from that time, we see from the geologic record sea level was much higher, okay, and the different distribution of plants, etc. So, but there were no people then, okay. So that confirmed, okay, that geologic record confirmed sea level rise, confirmed a lot of things that we project today, even though it's a different continental configuration, a lot of things were different.
Even now, the carbon dioxide, it is a good time, sometimes it's a bad time. There's fluctuations and so forth.
It's steady increase. I can track it to the oil crisis. There's a little slowdown to the 2018, to the crash 2008. Just a little blip. You can bet. I showed you the curve, the Mauna Loa curve. For me, I look at the little variations. You can see the collapse of the Soviet Union, everything. I can see in there, but you don't see it in the long-term trend. It's just little blips along the way.
One last question by Steve.
So, you testified that the academia has already reached some almost absolute consensus that anthropogenic climate change is
what I have learned from various people is that young people are the best communicators to their parents and their grandparents, okay? And so, I encourage you not just to communicate with the public, but with your family and with people, okay? What the future, you know, you can look at me and say, I didn't know any better, okay? I didn't have the knowledge, so you can blame me, okay? I didn't know any better, but now you know better, okay? So what do? You can't really blame me because I didn't know, okay? So so it's the communication about what it means, not just in the future, but there are opportunities in this to think about how do you develop new electric cars and new ways of powering, all these fantastic innovations. Okay, we're in the Nano Center, so all the new artificial photosynthesis, so many exciting new sciences have come up because of the need to deal with climate change. I'm thinking about reflective glass that reflects in the near-infrared. So if you're across the building from a building that's reflecting sunlight, it's not reflecting into your eye, right? Because it is reflecting in the near-infrared. So that's material science. That's a lot of exciting things are going on. Okay, so I'm hopeful that the science and the engineering scientists and engineers are taking this seriously. And we don't yet have the transformative technology to say, oh, this is how we take CO2 out of the air or something like that. But I think we are working in that direction.
Right. Let's thank Inez again.